All right, so while technically this lesson's continuing our look into the second derivative, it's really more a return to optimization problems, and which we have a few more tools if we want to use to solve these problems. But let's just get at some examples. And this one here, I believe we actually did in class at some point. Pretty sort of classic type of optimization problem. We have a piece of cardboard, a square piece of cardboard that's 3 feet by 3 feet. And we cut out a square of size X from each corner. And then the idea is we take this part that remains, we fold up the sides, and voila, we have a little simple open top box. And so I want to find the size of the square we should cut out. So the side length of X, because each of these squares here has a side length of X. What size of square, what length of X should we cut out so that we maximize the volume of this prism? And so first, the volume of this prism is the area of the base, which is a square, which is 3 minus each of these X's. So it's 3 minus 2x. So each side of that square is 3 minus 2x squared. That's the area of the whole square, times the height. And when you fold this up, the height of this box is just the length of that x. Now, if this was a question with no other requirements and no other steps and just asked to find the value of x for which we have the maximum volume, by far the fastest way of doing this would just be to notice graph this and find your maximum point, and then you'll be done. But usually this will be part of a number of steps to see that we understand potentially how this connects to derivatives. So I'm going to use derivatives for this. Before I differentiate, let me rewrite the form of this. I'm going to expand this perfect square and get 9 minus 12x plus 4x squared. All that's times x. Distribute the x. 9x minus 12x squared plus 4x cubed. So that's my volume function. I want to maximize this, so I'm going to differentiate this. So find dv with respect to x. I get 9 minus 24x plus 12x squared. And now I want to find the stationary points of this function. So I want this to equal 0. And again, you could just solve this by graphing at this point. I'll solve this a little more algebraically. I can take a factor of 3 out of this. And I get, if I rearrange this, take a factor of 3, I get 4x squared minus 8x plus 3. All that equals 0. This can indeed be factored. And so you get 2x minus 1 and 2x minus 3. So now I can algebraically, by looking at the factors, see my solutions. I have 2 solutions here, 2 stationary points. X equals 1/2 and x equals 3/2, which is 1.5. Now let's look at these solutions. This one here, if x is 1.5 or 3/2, I could look at the second derivative and figure out if that's a max or a min, or I could just use common sense and look at my little visual here. If this distance from here to here is 1.5 and this distance is also 1.5, that means I have nothing left in between. I've cut out the entire box. There's no box left, which I can do, but I have no volume. So this leads to a minimum volume. So I don't care about that. This is what I care about. This is what's going to lead to the maximum volume. And again, if I want, I could find the second derivative of this polynomial, which is a fairly simple polynomial to differentiate. Or I could just look at the graph of the function, or I could look at there's many options. But in the end, when x is 1/2 feet, I will have the maximum possible volume. All right, I have a parabola here, and this parabola is 4 minus x squared. And I have this rectangle inscribed inside it. Although it doesn't have to look exactly like this. It has to just be inscribed, which means it could look wide, it could be tall and skinny. That said, I want to find the dimensions of this rectangle so that it has the maximum possible area. And it all kind of hinges on this one point right here, because that point there, which I'll just call x comma y, I can imagine that point is somewhat tethered onto this parabola, and where would that point have to be so that my area is largest? And if we look at the wording of the question, we do want to find the value of x. So in the end, I just need to figure out where should that x value be to maximize this area. So I'm actually just going to focus, if I look at this little rectangle here, the area of that rectangle is going to be the same as just the x coordinate times the y coordinate. And so the area of what you see highlighted is xy. So if I look at the area of the entire rectangle, it's 2xy. So the area is 2xy. All right, I want to maximize this. And that said, I want to leave the x where it is, but the y, I want to write this in terms of x. And if you're not sure how, well, it says right here, y is the same as 4 minus x squared. Well, I wrote it right there. And so the y coordinate has to be on that parabola, which means that y coordinate has to be 4 minus the x squared, which means I can just rewrite this now as 2x times 4 minus x squared. And again, if we don't need to differentiate, we could just graph this and find the value of x where we have our maximum value. Again, though, I want to do a little differentiating, so I get 8x minus 2x cubed. That's my area function. I want to differentiate this with respect to x, so dA dx. Get a nice simple function, 8 minus 6x squared. And I want to make this equal 0 to find my stationary points. And so if I solve for x, I quickly, come back here. The iPad's fighting me. If I try this quickly, I get 6x squared equals 8, which means x squared equals 4/3, which means x equals plus or minus the square root of 4/3, or plus or minus 2 over root 3 to keep exact values. Which means when my x coordinate is at either positive or negative 2 over root 3, my rectangle will be at the largest size. And sometimes at times like this, you may want to reject the negative, but here x is a coordinate, x can definitely be a negative, so they're both good. And I've now finished the question, so because I'm just trying to find the value of x. So when x is either positive or negative 2 over root 3, or some variation of that number, then my area will be maximized. If I wanted to find the y coordinate, wouldn't be difficult. I would just put it into that equation there. If I wanted to find the area, it wouldn't be difficult. I just put it into here. But it doesn't ask for that, so I'm not. Lastly, another sort of classic optimization question, similar to the first one, now looking at a cylinder. And I have a cylinder that has a set volume of 1 liter. And I want to find the ideal height so that we minimize the surface area. So we have as little material as possible here. All right, well, first, let's think about volume. Volume of a cylinder is just the area of the circle times the height. But we know the volume. It's 1 liter. Now, I could put a 1 here. However, I do eventually want my height to be in centimeters. So I would like to kind of convert this liter into how it connects to centimeters. And one useful thing to remember is that a liter is the same as 1,000 milliliters, which is the same as 1,000 cubic centimeters. And since I want to think about this question in centimeters, I'm going to think my volume is 1,000 cubic centimeters instead of 1 liter. So I know that 1,000 equals pi r squared h. Keep in mind, this is not the function I'm trying to minimize or maximize. This is the volume, which is always going to equal 1,000. It's the surface area that I want to minimize. So surface area of a cylinder is the 2 circles, pi r squared, plus the lateral surface around it, which is the circumference times the height. All right, this is what I'm trying to minimize. And I do eventually want to know just the height. However, to go forwards, I need to either substitute my r's with an h or my h with an r. And regardless of what the question is asking, it's going to be a lot less work for me just to substitute this 1h in terms of r. And so I'm going to go back to my volume equation here and solve for h, which I can do quite nicely. If I get h equals 1,000 divided by pi r squared. And so I'm now going to take that and substitute it right there. And I get an area function that has just one variable for the input. I have 2 pi r squared plus 2 pi r times 1,000 over pi r squared. And this idea of having to combine 2 different functions together in order to reduce the number of variables is very, very common in these optimization problems. Well, now I have a function with just a single input. However, I can also cancel out my pi's here. I can also cancel out one of these r's. And so let me rewrite this as the surface area is 2 pi r squared plus 2,000 over r. Which, keep in mind, for differentiating, it's actually a little nicer if I write it like this. If I write it as, stop moving on me screen. If I write it as 2 pi r squared plus 2,000 times r to the negative 1. All right, I could take out a factor of 2, but I'm just going to differentiate this right now. And again, I could also just graph this function here and find the the minimum surface area. But let's assume we are trying to find this with derivatives, so pretty nice function to differentiate. dA dr is 4 pi r minus 2,000 times r to the negative 2, which, keep in mind, means 4 pi r minus 2,000 over r squared. And I want to make this equal 0 to find my stationary points, which means pretty quickly I can say 2,000 over r squared equals 4 pi r. And pretty quickly when I solve for r, I'll just skip the couple of steps, and I get to r equals the cube root of 500 over pi, which that's my exact value, but I'm going to decimalize this just because I want to think in centimeters with decimals, which is a bit more natural. So this is not my final answer yet. This is my radius. So I get the radius should be about 5.41. I'll put several significant figures down. That's the ideal radius that will minimize my surface area. And so now I need to find the height. And so don't forget, I have right here, height is 1,000 divided by pi r squared. So I can just take this answer I have here and squish it in right there. And so I'll kind of finish that off to the side right here. So therefore, height equals, or is approximately the same as 1,000 divided by pi times my answer down there, squared. You could also put the exact value in. And we pretty quickly get about 10.8 centimeters, which is accurate to 3 significant figures, which also notice is actually the exact same as twice the radius, especially if I kept more significant figures. Or I can say is the exact same as the diameter, which means if we want to minimize the surface area, we'd want the height of this to be the exact same as the diameter as this. That would minimize our surface area. But all good. And again, a fairly standard optimization question. I'm not saying it's easy, but there's lots like this, and there's countless variations.